So we're gonna do the derivative of trig functions with chain rule, because why not? Alright, so let's say we got a function such as 5 tan of 3x, right? This is like f of x, or just y. And so we want to find y prime, right? So how would we go about doing that? So that was a horrible y. Let's y prime. So we know the chain rule. We have the derivative of the outer times the derivative of the inner, right? So the derivative of tan x is secant squared. You should just know that. That looks like a 5. Let's try that again. That also looks like a 5. Oh well. So secant squared. And now what goes on the inside? Well, we have this 3x in here, and you keep the inside of the function, so we're going to keep 3x inside. And then we're going to multiply it by the derivative of the inner function. The derivative of 3x is 3, but we have this 5 out front, so 5 times 3 is 15. So the derivative of 5 tan of 3x is just 15 secant squared 3x. Next we're going to have f of, let's do theta, just because a different variable doesn't matter. You could use literally any variable as long as the function is in terms of that variable. So we have f of theta equals 1/4 sine of, or sine squared of 2 theta. And so we see we need to use this chain rule, right? And so the derivative of sine is cosine. So we can write that. So we could write cosine, and I'll just write f prime over here. F prime of theta. That's absolutely awful handwriting, I don't care. Alright, so cosine of theta, and then we keep the inside function, so 2 theta. I don't know why I did thetas. And then we have to multiply that by the original function, right? So we have this derivative of sine of cosine, right? And we have this 2, and so we bring this out to the front, so that's actually 2 over 4, or 1/2, and then we have to multiply it by the derivative of, or we just have to multiply it by the function, and this and the derivative of the inner. You can see this like multi-layered function thing here. We have this function. Let's see. We have this inner function, right? This 2 theta, and then we have the squared, and then we have the sine function. Like this multi-layered thing, so we have to do every single thing. So then we multiply that by the derivative of like sine of theta squared is a different function. So we'd have to say multiply it by sine, and then we still keep the 2 theta, and then 2, so we had this 2 over 4, and then we multiply it by the other 2, so we have this 2 and this 2 multiplied together, and 2 times 2 is 4 over 4 is just 1, so this is actually the answer. So we got y, not y prime, we got y is equal to Let's do sine of x squared. And so notice where the square is, because that is very important, because the sine function is not squared. It's the x that is squared before applying the sine function. Alright, so we will evaluate the derivative of the outer first. So the derivative of the outer function is sine, because we're squaring the x first. So, or sine, the derivative of sine is cosine. So we're going to write cos. And then we keep the inside function, so x squared stays the same. But the derivative of the inner function is 2x, because the derivative of x squared is 2x. So it's just 2x cos x squared. Alright, so we have the function y is equal to cos squared of pi x. So we want to find y prime, right? So the derivative of cosine is negative sine. So we could say so we could start with this negative sine function. But we can do some of this outer inner stuff first, so we don't have to come back to it. So the derivative of cosine squared is just 2, is negative 2 sine. So we could keep this negative 2 out front. And then the derivative of this function, of this function pi x, is just pi. So we could keep a negative 2 pi out front. And then the derivative of cosine is sine, as negative sine. So we could have this negative 2 pi sine, and we just keep the inside function, so pi x. And then we have to multiply that by the original function. So, or we multiply it back. So cosine of pi x. And that is our answer. Alright, let's try one last function. So we will have y is equal to let's make this a weird one. So we have the square root of x, and then we're going to add that to 1/4 sine of 2x, and let's just say sine squared for the fun of it. Alright, so we could rewrite this square root x in terms of the power. We could say this x is just, we could just rewrite this and say, nope, we don't like that. We like x to the 1/2 in calculus, because it makes math easier. It makes the power rule easier. So we know how to differentiate this. We could use the power rule, right? So we could just say the derivative of the x to the 1/2. We bring the 1/2 down, so that's negative 1/2. Right, so we say 1/2 to the, and then x to the negative 1/2 power, which we can then rewrite and radical notation. We could say 1/2. We could just say, I'm going to write this in blue because I can, because it's in like proper radical notation. We're going to say 1/2 square roots of x. Alright, so now back to this sine business over here. So we know that the derivative of sine is cosine, and so we could write so I will write cosine, and then we know to keep this inside function, so 2x, and then we know to multiply it by the derivative, or we need to multiply it back by sine of 2x, because that's just how these trig functions be sometimes. And then, just like the other one, this 2 and this 2 are multiplied to get 4, and so this 1 over 4 just becomes 1, so it's just this 1 over 2 squared of x and cosine 2x plus sine 2x. I know I said that was the last one, but there's one more I want to try. Alright, so we're going to do one more function because I want to showcase a function inside of a function. And so we're just going to say sine x of tangent x. So we got sine of tan of 2x. And so this is a composite function, and I'm actually going to write out some of the steps because this is kind of long and complicated. So we have y prime, and so we know that the derivative of a sine is cosine, and then we just stick the inside function in there, tan of 2x. So that part is easy. Alright, this goes to cosine, and this part remains the same, but it's not that easy because we have to multiply it by the derivative of the inside function. So we're going to say times the derivative, and I'm just going to say dy dx of tan 2x. Alright, so I'm now just going to be working on the blue function. So the derivative of tangent secant squared, the derivative of tangent is secant squared. So we're going to say secant squared, and then remember keep the inside function, so 2x. And so the derivative of tan x, like with the other problems, or tan 2x would be secant squared 2x times the derivative of the inside function, which is just d dx of 2x, which is just 2. So 2 secant squared 2x is this derivative. And so then once you just fix everything together, I will write the final answer in blue. So we're going to say equals, all this is equal to, we'll bring the 2 up front, we're going to say 2, and then I like keeping this cos tan at the front because I said so, because I did it first. Cosine tan of 2x, and then we just multiply by this secant squared to x that we just solved. We pull this 2 up front, so we don't need that. And so I'll write that in blue to show where we got that. So we got secant squared uh, 2x. And And while that was a bit complicated, it's not too bad, and it's doable. Just break everything down.